this first example, I want to find the other, spelled that wrong, the other 5 trig values when cosecant is -5/2 and theta is in quadrant 3. Okay, so lots of things to keep track of here. We're going to be utilizing the fundamental identities again. And we also want to make sure that we keep in mind our diagram for the signs of the trig functions, A, S, T, C. That will help us out also getting our positives and negatives down, especially for quadrant 3 in this case. Okay, so theta is in quadrant 3, the cosecant is -5/2. Well, I know first of all that the sine is the reciprocal of the cosecant, right? So a reciprocal identity can be helpful. And in this case, it's going to be 1 over the -5/2. Of course, multiplied by the reciprocal, the answer will be -2/5. Right? So the sine is -2/5. That's one answer. Okay. From that, I can also determine the cosine. Once I know the sine, I know that the sine squared plus the cosine squared is equal to 1. So I could use Pythagorean identity, plug in the sine, square it, and solve for the cosine. So sine squared would be -2/5 all squared plus cosine squared equals 1. -2/5 squared is 4/25. Now, because I have a 25 as my denominator here, I'm going to get a common denominator with my 1. I think this is a useful trick to do in advance when you see these kinds of problems showing up. Just get common denominators across the board right away, and it saves you a little bit of effort later on. So I got 4/25 here. 1 is actually 25/25, right? Okay. And then I can subtract off my 4/25. Just kind of makes things look a little bit nicer. 25 minus 4 is 21/25. So I have cosine squared theta is 21/25. And then I need to take the square root to solve for the cosine, right? So the cosine of theta is the positive or negative square root of 21/25. Remember, this is something called the square root property. You may have learned this, hopefully you learned this in an algebra class before, but anytime you have x squared equal to a variable squared equal to a constant, the solution is going to be both the positive and negative square roots of that constant. If you had x squared equals 9, then positive and -3 are both solutions. And so in this case, you want to include both the positive and the negative. However, we're looking in quadrant 3. Well, what is the sine of the cosine, SIGN, of the cosine in quadrant 3? Well, tangent's positive, but the cosine then would be negative, right? So I'm going to focus in on that negative value because of the quadrant we're in, right? So quadrant 3 determines the sign that we're using there. So the cosine of theta is going to be the negative. Now, the square root of 21 doesn't simplify, but the square root of 25 does. So if I split that root up, I end up with just a 5 on the bottom. Negative square root of 21 all over 5, okay? So that gives me the cosine value. Now I can also find the secant value, double check, yeah, secant value directly from this, because the secant, SEC theta, is the reciprocal of the cosine, so I can basically flip that fraction, right? So it's -5 over the square root of 21. But remember, we never want radicals on the bottom, we want to rationalize denominators. So I'm going to multiply top and bottom by the square root of 21. And that will give me for the secant -5 times the square root of 21 all over 21. Okay, so there's our secant value. So that gives me, what, 3 of my values. I still need the tangent and the cotangent. Utilizing our fundamental identities for the tangent and the cotangent, you could potentially use Pythagorean identities. I would probably at this point use my quotient identities. So for the tangent, I know that the tangent is the sine over the cosine. And so, let's see, I know the sine, did I erase it already? I just did. Well, okay, the sine of theta was negative 2/5, right? It was reciprocal of the cosecant, that's not too bad. Yeah, so let's not erase that, let's keep that guy. So I know the sine is negative 2/5. I know the cosine right here is negative square root 21 over 5. Multiplied by the reciprocal when I divide fractions. So this is negative 2/5 times 5 over, I guess, negative root 21. There's a double negative, so the negatives cancel. There's a 5 on top and a 5 on the bottom. Those cancel. And we'll be left with 2 over the square root 21. And of course, again, I have to rationalize the denominator, so multiply by root 21 on top and bottom. And that gives us a tangent value of 2 root 21 all over 21. Okay, so there's our tangent. And then, of course, the cotangent is merely the reciprocal. Oh, and I also want to make sure I get the sign right, the SIGN, right? Positive, negative. The tangent is positive in quadrant 3, so I want to stick with a positive value there. Which will always play out when you do, if you do the signs right here, because the double negative creates that positive. The cotangent is also positive because it's the reciprocal, and since it's the reciprocal of the tangent, I just take this answer and flip it. The problem is, when I flip it, the root goes to the bottom and I have to re-rationalize. Instead of doing that, what you could do is actually go to the previous step where the root was on the bottom, flip that one, and you'll get the rationalized form. So I would actually take the 2 over root 21, flip it, and you get root 21 all over 2 as your cotangent value. A little bit easier that way, rather than taking the rationalized form, flipping it, and then rationalizing again and having to reduce. You'll still get this value, it's just fewer steps to go through, okay? So that utilizes several of our steps, right? Or several of our fundamental identities. It utilizes our Pythagorean identity. We used some reciprocal identities and quotient identities here. So it gets us a lot of them. We didn't use the even odd identities here, but that's okay. We don't need them we won't use them if we don't need them. So there's other identities that would have worked. Like I said, we could have gotten the tangent by utilizing a Pythagorean identity with the secant squared. We could have done that. There's a variety of different routes you could take. So don't just think that any one particular method is the best or the only one. Sometimes, like this one, I think probably is best solved without the extra Pythagorean identity, because I think the Pythagorean identities take a little bit more work. But again, it's not the only way to solve these.